I have good news and bad news and bad news and good news. The good news is this pen here started working. And the bad news is in the process it exploded all over me and now I'm blue. The next bad news is I already did this entire video, focus, I already did this entire video, but it recorded in time-lapse or something, so there was no sound and it was 4x speed. And I guess the only good news there is that now I get to do it again, and maybe I'll do it better. I don't know. Let's get going here. The idea for this video is and was polyprotic aqueous acid dissociations. We talked about monoprotic, which is one hydrogen. Polyprotic, I mean the word's right there, polyprotic, so more than one. And then this is proton, so we're going to say acidic. That didn't go well. More than one acidic hydrogen. So if we're looking at monoprotic species, which is traditionally what we've seen, at least so far, you think of things like HCl, which has one H, or HNO3, which has one H, or maybe something less obvious like what I'm going to write in a minute. Then you might have something that's diprotic. Something like H2SO4 or H2CO3 sulfuric or carbonic acid. Diprotic because they have two hydrogens that can be removed. And as a result, you end up with an amphoteric species as soon as you remove one of those protons. Then maybe you have something that's triprotic, like phosphoric acid, H3PO4. And there are three hydrogens that are acidic. Now, just because you have multiple hydrogens doesn't mean all those hydrogens are acidic, right? And an example of that might be acetic acid, CH3COOH. It looks like there's four H's because there are, but they're in different locations, and it's just that last hydrogen that is the acidic hydrogen. It's only monoprotic. And you can kind of see that if you draw the structure out, which I know I've done in other videos, but a quick glance here, CH3, C double bond O, OH. That one H is different than the others, and that's the one that can be removed right there. And the other three are attached to the carbon, and that's a big deal to try and remove those, and the topic for another video. So what we're going to do here with this video, for these aqueous dissociation equations, I'm going to do two examples right now. Both of them we're going to start out with 0.500 molar acids. So we'll just set up our parameters here. 0.500 molar aqueous solutions. And we'll say they're at 25 degrees Celsius, so we can use kW as 10 to the minus 14th. And I'm only going to be looking for the concentration of species at equilibrium. And we'll also be looking for a pH. And very easily, if you have this concentration of species at equilibrium, you can get a pH, but we'll just set some parameters so that we feel like we've done something by the end. All right, let's get a jump on this. We'll start out with a strong diprotic acid, H2SO4. And so, pretend we're given here 0.500 molar H2SO4. We're looking for that stuff right there. So just like any other equilibrium problem, start out by writing the aqueous dissociation equation. We've got H2SO4 in water. We're going to get the hydronium ion and the sulfate polyatomic, and the hydrogen sulfate polyatomic ion. I snuck that in. It's not very pretty, but let's fix that ever so slightly. No one will notice. All right. And the hydrogen sulfate polyatomic ion. We have a Ka expression to write, and that is the concentration H3O plus, SO4 2 minus, HSO4 minus. And the Ka value that we can get from a table somewhere is large. And the significance of that, as you may recall, is that this is a strong acid. And strong acids dissociate completely. And as you look at the previous video, you may recall that, like, if the K value is large, it dissociates completely, and the problem becomes much easier. But we're going to show all the work because this example is special and the next two aren't as easy. All right, so we've got our ice problem starting out with what's given, 0.500 molar from the given. Not worried about the H2O, pure substance, H3O plus. Auto-ionizes to give 10 to the minus 7th molar H3O plus. And we haven't made any of that yet. Once again in slow-mo, given. Before the H2SO4 dissociates, this is how much H3O plus we have from the water dissociating, ionizing itself. And we haven't made any HSO4 minus yet. Since this is a strong acid, it's going to dissociate completely. So initially we have that much. The change is going to be all of it. We're going to lose that 0.500. Correspondingly, we're going to gain that 0.500, and we're going to gain that 0.500. And we get our equilibrium conditions, which is 0 molar, and that's kind of a lie, and 0.500 molar, and 0.500 molar. And I want to pause there and go back and look at this. You don't have 0 in equilibrium expressions, but since this is a large number, this ends up being a really small number when you do the calculation. So for practical purposes, it's a 0. That's that step. Now what we need to do in these problems is come up with a stepwise dissociation, all right? In a stepwise dissociation, you take off one hydrogen at a time. And so we took one off of H2SO4 and made HSO4 minus. And now we're going to take one off of HSO4 minus and make SO4 2 minus. HSO4 minus in water, giving us H3O plus and SO4 2 minus. Our Ka, which I will declare as Ka2, just like that was Ka1 for the second step here. We're going to have the H3O plus again, and the SO4 2 minus this time, and HSO4 minus. And here's where things get a bit different, because this has a value, a K value of 1.2 times 10 to the minus 2. And that becomes an indication we have a weak acid. And what it means to be a weak acid is that it does not dissociate completely. And so our change isn't going to be all of it. In fact, I'll set this up. HSO4 minus. We didn't start with any, but we ended up with some. So this is the number we're going to put down there. 0.500 molar. All right, it's stepwise. We took one off, one of the protons off, and we ended up with this. So in the next step, that's how much we're starting with. We made some H+, that's how much we're starting with, and we haven't made any of this yet. Our change here was all of it because it's strong. Our change here doesn't get to be all of it because it's weak, so we're going to lose some unknown amount and correspondingly gain that same unknown amount on the other side, giving us equilibrium conditions with 0.500 minus x, 0.500 plus x, and x. Then when we solve for our Ka2, should be 0.500 plus x times x, that's this and this from our products, over the 0.500 minus x of our reactant, and that should be 1.2 times 10 to the minus second. If we solve for that x, which is our concentration change, it ends up 0.072 molar to 2 sig figs. And now we have all the information we need. What species do we have here at equilibrium? And this is kind of a useful step to pay attention to. The way I would recommend handling it, and I'll do this with a highlighter maybe so we can see it, is what is present in your equilibrium solution is this stuff here. I just banged my face into the camera. And we need to look for things the last time we see them, because that's the last change that has happened to them. So this is H2SO4. I won't see it ever again, so I need that number right there. This is H2O, and I don't care about it, because it's a pure substance. H3O+, I see as a 0.500, But then I see it again later as a 0.500 plus X. So that is the number I'm going to need. HSO4 minus I see as 0.500, but later I see it as a 0.500 minus X, so that's the number I'm going to need. And then I never see SO4 2 minus until we get there. So those four things are for sure going to be part of, or going to be the main components of our final solution. Let's get some answers over here. In our final solution at equilibrium, we're going to have the H2SO4 and the HSO4 minus, the SO4 2 minus, H3O plus, and not to be outshone, anytime you have H3O plus, you must take into consideration that there is OH minus. And we saw that in a previous video, but we're going to have to deal with this concentration of OH minus. We'll calculate that using our KW expression, H3O plus times OH minus, which is equal to 10 to the minus 14th at 25 degrees Celsius. So this will be KW over our concentration H3O plus. Okay. If we look back here at our stuff, luckily we've made a list of what we have. H2SO4 is supposed to be 0.5, or sorry, it's supposed to be 0 molar. Okay, in fact, I'm going to set up a bit of a table here to budget space better. So let's put this, and this is going to be our answers for part A. H2SO4 is supposed to be 0 molar from that. And again, a lot of times you'll see books that don't list that, or maybe a professor or a teacher doesn't list that. That's fine. I mean, it's true for simple mathematical purposes. But I like to see it because what we're saying is this was here. This is where everything came from, and there's still a negligible amount of it present. So this is going to be 0 molar H2SO4. All right? HSO4 minus is supposed to be 0.500 minus X, and that should end up 0.43 molar HSO4 minus, because our X is 0.072, all right? 0.500 minus 0.072. Our SO4 2 minus is supposed to be X, and that is 7.2 times 10 to the minus 2 molar. And then we've got our H3O plus, which is supposed to be 0.500 plus X, and that X is 0.072, so we should end up with 0.57. And then our OH should be 10 to the minus 14th over this 0.57, and that gives us 1.8 times 10 to the minus 14th molar OH minus. And that right there is our part A. Our part B was to get a pH, and so we'll just sneak that calculation in very quickly. pH is supposed to be the negative log of our concentration H3O plus, and since that was 0.57, we end up with a pH of 0.24. And that is sulfuric acid. And the reason that's special is because sulfuric acid is a common acid. It is a common strong acid, and it is the only common strong diprotic acid. So that first step, everything dissociated. And you can kind of plan ahead now that for our second example, we're going to have something that does not have a strong first step. And that, in this case, is going to be sulfurous acid point. On the one hand, it's not great that I would choose something that looks so similar, but on the other hand, I want to choose something that looks similar so we can see the significance of this strength as we look ahead at future videos that talk about like why an acid or base might be strong. We have to do this same process, all right? We're going to write this aqueous dissociation equation in 2 steps. It's stepwise, right? Write our K expressions and everything else. In fact, let's take care of business. All right, no surprises there. I put Ka1 because I removed an H, and I'm going to do it again. A common question that comes up is like, how do I know when to stop? And the answer is when you run out of H's. All right, so like monoprotic ones, you run out of H's after that first step, if you're paying attention. Diprotic, you're going to have to run out of H's after that second step. Triprotic, 3 steps. And in the next video, I do phosphoric acid as one of these calculations, which gets a bit tedious, but there's some shortcuts and some math involved that might save us some effort. We've got a K value from a table for this of 1.4 times 10 to the minus 2. All right. Now that is important information. That tells us that this is weak. So while this was a large value, it told us a strong acid, this is a weak value, or sorry, a small value, smaller, which is telling us it's a weak acid, and things have now changed. We're going to start with our 0.500 again. Still not worried about the water. Water still auto-ionizes, and we still don't have any of that. But now instead of all of it changing, we're going to only have some of it. And I don't know how much that is. So we use an X, right? And then right here, we're going to gain that much, and we're going to gain that much. And then our equilibrium amounts, 0.500 minus X, and X, and X. And this is what we're working with in that first step. Now we know it's going to keep going, and let's see how that works. We've gotten to the HSO3 minus, and now we're going to take that HSO3 minus. The pen semi-visible. Alright, there's our aqueous dissociation equation. If you look back at previous videos, all we're doing is taking an H off. We have a Ka2, that value will come from a table. The Ka expression, though, we are chucking out there without much effort. And again, this came from a table as 6.5 times 10 to the minus 8th. And if you're paying attention, just like we did before, this is weak, right? In fact, it's weaker. Significantly weaker. That was a 10 to the minus 2, and that's a 10 to the minus 8th. And let's make some space. Same situation we had before, where I had some of this that came from the first step. So that is our X now. This came from that first step, and I have X. This is still 0, and that's still a pure substance. Now, what we need to take into consideration is, this is weak. We're not going to dissociate all of it. I don't know how much, and I'm going to pretend for a moment that I don't know X. Now, I realize that may make some people uncomfortable, so we'll just pretend I already know X, that I've solved for it. Oh, it's X squared, 0.5 minus X, equals 1.4 times 10 to the minus 2. That's our quadratic. And then we plug it into the calculator and we find out X equals a number that I don't feel like writing right now, because I'm just going to use a different variable here. So we'll say our change is going to be, I don't know. And it's a Y this time because I already used X. We'll gain Y and we'll gain Y. And we end up with X minus Y, X plus Y, and Y. To be clear, we do know what X is. This math will get us the value for X. It's faster to write this, and I can show you a little trick that saves us some effort. If we're looking at Ka2 now, just like we did with that, H3O plus is supposed to be X plus Y. SO3 minus is supposed to be Y, and HSO3 is supposed to be X minus Y. Now these two things don't cancel out except for one important fact, and we'll see this fact significantly in the next video, and that fact is X is going to be much greater than Y. And I'll write that maybe here. X has to be much greater than Y. I want to make sure that's on the screen. Sadly, my paper is taped to the bench, so X is much greater than Y. And the reason we know that is this wasn't very strong, and it gave us this tiny amount. This is way weaker, and it's going to give us an even tinier amount. So x plus y is going to approximate as x, and x minus y is going to approximate as x, because x is so much bigger than y. So we end up with x times y over x, which is y. Our Ka2 is y. That means that y equals 6.5 times 10 to the minus 8th molar. I didn't need to know x to do that, and that's why I held off on calculating x, but now we'll just wave our hands in the air as if I calculated it, because I did, and that is 7.7 times 10 to the minus 2 molar. So there's our x and our y. Those are fairly useful numbers. Up here, x was all of it. Up here, x was 0.72. Now we got our x and our y right there. And let's list out what we've got in our final solution and finish this problem up. At equilibrium, we're going to have the H2SO3, the HSO3, the SO3 2 minus, the H3O plus, and we cannot forget the OH minus. We said we're going to get that as Kw over concentration H3O plus every single time. These are going to be based on what we see over here. And the tip that I gave before was that if you go down the side and across the bottom, you'll hit all of the values you need. My dog's hacking over there. One of them peed on my car during the last video. This has been a very exciting day. 0.500 molar turns into 0. This number here is the last time I see the HSO3 minus, right? It's nowhere else. If I'm looking at H3O plus, though, I can see it right there. So this must be the value that I need. If I'm looking for the HSO3 minus, the last time I will see it is right there. So that must be the value we need. And if I'm looking for the SO3 2 minus, that is the last place we see it. And that's what we're going to have over there. Our H2SO3 is supposed to be, did I say all of it? It's not all of it. 0.500 minus x, and x is 0.77, so we should end up with about 0.42 molar H2SO3. All right. Our HSO3 minus is supposed to be x minus y, but x is way bigger than y, right? In fact, we can see it right there, 10 to the minus 8th versus 10 to the minus 2. So we should just end up with x, which was 7.7 times 10 to the minus 2. Ooh, I committed a great sin there. I forgot my minus sign. SO3 2 minus is supposed to be y, and y is 6.5 times 10 to the minus 8th. And then our H3O plus should be x plus y, which is, for all practical purposes, x, just like x minus y was, because y is so small, and that is 7.7 times 10 to the minus 2nd molar. We've got the OH minus, which we'll calculate as our 10 to the minus 14th over the 0.077 that we calculated right there. And we end up, in this case, with 1.3 times 10 to the minus 13th molar OH minus. So we've got those things. That is, at equilibrium, our concentration of all the species, part A. And a couple things to note. In a polyprotic dissociation, starting with something weak, Ka2 will always be your Y value. Every single time, it doesn't matter what you're working with. If you're starting with a weak polyprotic, in that second step, Ka2 is always Y. And that's the reason why that math right there. When you look at a triprotic, that's still true, but then the third step doesn't have that same shortcut. We still need to get our pH, and we'll calculate that as the negative log, concentration H3O plus. And we've got that right there, 0.077, and that gives us a pH of 1.11. And that's our answer to part B. So we do see some obvious correlation here. H2SO4 is a strong acid, and we get a lower pH, right? It's a more acidic solution. H2SO3 is a weak acid with that K value, and we end up with a higher pH, a less acidic pH. And we'll take a look at what happens when you have 3 H's in the next video.